Eaves Council of Canada's 2020 Technical Series. In today's episode on the cost of building enclosures, we're jumping into part 2 of our series. This is the series based on the comparative life cycle analysis completed by RDH. Principal author was Dr. Randy Van Straten, peer review and stewardship provided by Dr. Ted Kessick, and on behalf of the Eaves Council, its president, John Garbin, and myself, Peter Collier, on behalf of the Eaves Council's Technical Committee. A quick observation of our standard copyright and disclaimer notices. And let's get started. And we're into part 2 of our 3-part series. If this is your first time joining us, I would encourage you to go back and have a look at video 1 for basic terminology and study framework, or have a look at this video's description where you'll find a link to the companion booklet for the series. The booklet will take you through the terminology, as well as other aspects of the study. As previewed in our previous installment, in today's installment, part 2, we will be looking at energy codes, construction requirements, thermal modeling, and related energy use, beginning with our residential property. Our residential building is a standard 6-story wood frame building with 40% glazing. No balconies or terraces were included, however, and that was to match the typical construction and styling of our commercial building and limit the number of variables between the two. Turning first to the wall construction for our eaves wall assembly, we have standard wood frame construction inboard of the eaves. Looking at the eaves components themselves, we have a vapor permeable, fluid applied air and moisture barrier, trowel applied adhesive, no mechanical fasteners used, a profiled expanded polystyrene insulation, that is a grooved insulation board, a base coat, standard mesh, and the finish coat. Expansion joints were incorporated at each floor line. The design of the system corresponds with the requirements of S716.3, which is the eaves design standard, and installation followed as per S716.2. No changes in design or construction methods were needed or applied to this eaves wall assembly to achieve the target whole wall R values that would be met by the other assemblies. So how did our wall assembly do? I'm going to spend a little extra time on this view as it sets the stage for the balance of our residential assemblies. On the top row, we have our 4 cities and our high R wall. Below that, we have the applicable energy code's prescriptive requirement for each location and the high R wall value. You may notice that all the cities, with the exception of Montreal, base their requirements on clear wall R values, whereas Montreal bases its requirement on the nominal value. To conform to these requirements, as well as S716 design and installation standards, we have our related CI insulation thickness, that is our expanded polystyrene insulation, below that, and the corresponding R value for that insulation. Our wall assemblies were then placed on our archetypical building and modeled to determine the whole wall or effective R value, which is the figures along the bottom row. So 2.6 for Vancouver, 2.8 Calgary, 2.6 for Toronto and Montreal, and our high R wall coming in at a 7.2. Turning now to the wall construction for our masonry veneer, construction methods reflected those that are most common in the Canadian marketplace. Where we depart from the norm is through the use of thermally optimized screw-back brick ties with stainless steel hooks and the use of standoff galvanized steel lintels and shelf angles at each floor line. This is not considered common, but was necessary in order for the masonry veneer to meet the target whole wall R value as established by our eaves wall, in particular as it relates to the high R wall. The masonry performance was recorded as follows. Along the top row, we have the target whole wall R value as established by our eaves. In the bottom row, we have the whole wall value as achieved by our masonry assembly. Between the two, we find the CI thicknesses required for the masonry assembly to achieve that whole wall target value. So 2 inches in Vancouver, Toronto, and Montreal, 3 inches in Calgary, and 7.5 inches for the high R condition. A quick look at the wall construction for our fiber cement cladding. As per the previous assemblies, we have typical backup wall construction, and outboard of that we have typical wood frame construction. Where this assembly may differ from what you're used to seeing is through the use of 3-inch wide by 3/4 inch wood battens. This allows for the holding of the insulation without the use of additional securement methods such as impaling pins or other fasteners that may contribute to thermal bridging and heat energy loss. This method is optimal and provides for only 2 to 6% degradation, and the battens provide a good solid nailing surface for cladding to be attached to as well. In summary now, for the residential assemblies, we have RSI values of approximately the same for eaves, brick veneer, and fiber cement cladding in our 4 subject cities. Where we do see some differences in the required CI to achieve our high R values: 4.3 for eaves, 4.6 for the fiber cement cladding, and an RSI value of 5.3 for the brick veneer. So the next few slides will explore how the assemblies go from a base wall value that includes an R21 batt insulation plus an average of an R8 on the exterior, yet we end up with a whole wall R value that is about half of the beginning nominal. So how did we get from nominal to whole? What was accounted for? Where were the losses? That's what we're going to be exploring in the next few slides. Looking now to Vancouver and the effects of each of our considerations on the nominal value, we look at clear wall, floor to wall, mechanical attachment effects, and lastly, the impact of window flanking. As you can see, starting with an average nominal value of 5.2, we end up with a whole wall R value of approximately 50% for most assemblies at 2.6. The outcome for Calgary, while the values are higher than what is required for Vancouver, the pattern is very much the same. Slight drop in the masonry assembly from the nominal to the clear wall, slight drop again from the clear wall to the floor to wall considerations, some impact by the mechanical attachment for both the fiber cement cladding and the masonry veneer. However, window flanking once again emerges as the single largest influencer of thermal performance in our modeled conditions, where we see the biggest drop in overall performance is once window flanking is taken into consideration. So again, we have a nominal value and a whole wall R value with a difference of approximately 50%. Looking now at Toronto, we have a lower nominal value to begin with relative to Calgary, and we see the same sort of pattern with regard to stepping down from nominal to clear wall to floor wall, etc., until we get to our whole wall R value, which is about a 50% drop from our starting point of 5.2 to 5.3. Montreal, again, we see the typical profile where we begin with a nominal value of approximately 5.3 or 5.2 on average, and have a whole wall R value of about 50% less at 2.6, pardon me. Our high R wall, we begin with a nominal value once again and end with our effective R value. But in this case, we don't see the same percentage change from our nominal value down to our whole wall R value. We go from, in the case of the fiber cement cladding, from an 8.3 to a 7.2. So the curious among you may be asking, why is that? Why don't we see the same percentage drop from nominal to whole wall when dealing with a high R assembly? Without getting into too much detail, I'll refer you back to part 1 of this series where we looked at terminology and specifically the impact of continuous insulation and its mitigation on thermal bridging. One of the other benefits of exterior insulation is the lifting, if you will, of the effective thermal resistance of all of the insulation inboard of it. What we also see with higher insulation amounts on the exterior is a reduction in the impacts of mechanical attachment losses through that insulation. So the thicker the exterior insulation, the better the overall wall assembly performance translates into. All right, so now we're able to move on to our commercial building, again, a 12-story commercial building, and our same cities and the same target high R wall value. So beginning with our eaves wall construction, we have the same components as utilized in the residential wall assembly. Where we differ here is through the use of metal framing and mineral wool insulation, this time at an R14 as opposed to an R21, and also that the eaves assembly is prefabricated. That is a panelized eaves assembly that arrives on site in a unitized fashion and is installed that way. The assembly and modeling also allowed for through-wall flashing at each floor line. While typical in, let us say, Western Canada, it's not considered common practice across all of Canada, but nevertheless was modeled in all of the assemblies, regardless of the location. As with our residential condition, we begin with the performance of the eaves and all things to be considered in order to establish our target whole wall R values for the other assemblies to meet. So we have the requirement along the top row for Vancouver, Calgary, Toronto, Montreal, and our high R wall, which remains at 40, the required CI thickness of the eaves wall assemblies, the corresponding CI R value, and then the modeled values, which establishes the target values for the other assemblies to reach. 2.1 for Vancouver, 2.8 for Calgary, 2.3 for Toronto, 1.8 in Montreal, and a 7.3 RSI value for a high R wall. Turning now to our masonry veneer, we have the same arrangement of materials as seen in the residential assembly, with typical commercial options being used for our framing, exterior sheathing, and an adhered membrane. As with the residential assembly, the loss of heat energy through shelf angles and lentils is minimized through the use of standoff technology. We also have our thermally optimized brick ties. None of these are seen, or neither of these are seen as common practice in the Canadian context, but necessary in order to meet the whole wall R value target established by our eaves wall. While the construction's been optimized with regard to thermal performance, some constructability challenges did emerge, specifically with regard to structural integrity. With the exception of the Montreal assembly, the exterior insulation requirements translates to the face of the veneer being some 11.5 to 16 inches outboard of the supporting structure. This led RDH to comment the following, or make the following comment in the report. Few brick tie options are currently available to accommodate CI thicknesses for Vancouver, Calgary, Toronto, or the high R wall cases. These walls may not be structurally feasible. As noted in our previous tables, we have the whole wall target value as established by the eaves wall assemblies in our top row. So for Vancouver, 2.1, Calgary, 2.8, Toronto, 2.3, Montreal, 1.8, and for our high R wall, an RSI value of 7. In the bottom row, we have the whole wall value as achieved by the masonry wall assembly. In between the two, we have the required CI for the masonry assembly in order to achieve the whole wall target value. So for Vancouver, 6 inches, Calgary, 6.5, Toronto, 8, and Montreal, 3. For a high R wall, we have an exterior insulation thickness of 10.5 inches. The wall construction for precast panels represents the most common approach to precast construction in the Canadian marketplace. So we have our precast panel, and unlike our other assemblies, our continuous insulation in the precast context is on the interior side in the form of a sprayed polyurethane foam insulation, a 2-pound to be more specific. Inboard of that, we have the metal framing members hosting our bad insulation, which is an R14 mineral wool, then our drywall, and no polyethylene vapor barrier required here. The precast, between the precast and the floor slab, you'll also see that there is a 2-inch fire-stopping mineral wool insulation or safing insulation. This amount of insulation at this location is not considered common in the Canadian marketplace, but was utilized here again to optimize the thermal performance and, in the case of precast, mitigate the effects of floor-to-wall interfaces. The table of results now for the precast wall assembly. Not unlike all of our other assemblies, and as with the other tables, we have our whole wall target value along the top row, and then the whole wall, not target value, but the whole wall value as achieved by the precast assembly along the bottom row. In between, we have the related CI thicknesses for our various locations in our high R condition. You'll note in Calgary, we have a 7-inch SPF requirement, and in the high R condition, a 9-inch SPF condition or required thickness. I'll talk about that in a little bit more detail because it does factor into some of the costing considerations in our later material. The wall construction for the aluminum composite panel system will look very familiar to those experienced with these sorts of materials. What may look different is the clipping system, in this case a Cascadia clipping system, which is a fiberglass clipping system selected for its thermal performance, which is optimal in this sort of assembly, 6 to 9% degradation, which is better than what you would see for this sort of assembly and discrete clipping systems, or intermittent clipping systems, as they're sometimes called, utilizing aluminum or even stainless steel. So an optimal assembly in terms of thermal performance for aluminum composite panel wall assembly. And that's reflected in the table of results here as well, where we see insulation thicknesses in the range of our exterior insulation and finish system, slightly higher for Calgary and our high R wall condition, but less than what we see for masonry and our precast wall assemblies. So looking now in summary at the required CI for various assemblies in order to meet the target R value as established by our EIFS wall assemblies, you can see the range in thicknesses for the various locations and our selected wall assemblies for brick veneer, precast, and AC panels. What you may notice is that the range of, or the variety of insulation thicknesses needed to meet the target R value across the alternatives is much broader than what we saw in the residential examples. That's for a variety of reasons, but suffice it to say for now that the reason for that is the commercial envelopes are more thermally sensitive, if you will, because of the effects of thermal bridging through the metal framing members. So, of course, we have a difference in the exterior insulation amounts required and a difference in performance across these assemblies as well. This is that same CI information as looked at in the previous chart, except expressed in millimeters. And I wanted to spend some time looking at the various thicknesses of the insulation on this slide for a couple of reasons, mainly as it relates to the SPF application thicknesses for Calgary and our high R wall. As you look at these thicknesses, they are at 178 and 229 millimeters. If we're applying the installation standards for other assemblies to our scenarios, it's fair to apply the installation standard for the SPF in our precast condition. So when we look at the SPF installation standards, we have a maximum single pass thickness of 50 millimeters. A cooling period of no less than 10 minutes is required between the first and second application. No less than an hour period must be allowed for or prior to the application of a third coat. If an additional pass is required, and a cooling period of 1 to 4 hours is required, and that would be the cooling periods required to achieve our 7+ inches in the Calgary condition. For the high R, where we are exceeding greater than 8 inches of SPF, there's a minimum 12-hour cooling period required. It's not believed that these cooling periods were accounted for in the initial or upfront construction costs for the high R or the Calgary condition. It would appear in the costing tables that the differences in the high R relative to other locations is only a difference in the material costs and does not reflect the non-productive labor activities associated with cooling periods, mobilization, and demobilizations. The next few moments will be spent on the thermal resistance of our commercial wall assemblies, exploring where we lost heat energy in our various wall assemblies in our various locations and in our high R wall condition. Turning first to Vancouver and our commercial wall assemblies, beginning with the nominal value and working our way down to our whole wall R value. As you can see, the impacts of our clear wall considerations, our floor to wall considerations, mechanical attachments, and window flanking, the effects of thermal bridging are more pronounced in the commercial examples than they were in the residential examples. So a greater impact through things such as mechanical attachment into metal stud than the same attachment method into a wood framing member. In Calgary, even a greater percentage drop from our highest nominal R value of 9.9 down to a 2.7. So this represents about a 73% drop in R value when we look at the difference between nominal and our whole wall R value. Of course, the target whole wall R value is about the same, 0.1 difference across our various assemblies for Calgary. Continuing eastward now to Toronto, we see the same sort of pattern that we saw in Vancouver and in Calgary, but just not as pronounced when we look at the differences between nominal value to clear wall to floor to wall, mechanical attachment considerations, and lastly, the impacts of window flanking. More dramatic effects in terms of thermal bridging and whatnot for each of those particular considerations relative to the same considerations in the residential context. A quick look at the Montreal example, where we see the same pattern in terms of behaviors with regard to the R value and stepping down from our nominal all the way down to our whole wall. So starting with a slightly lower value, remembering that Montreal bases its requirement on nominal values as opposed to clear wall R values. So we begin with a nominal value of approximately 3.5 for the brick veneer assembly and for our AC panels. And then we see the typical reduction in that nominal value through the effects of repetitive framing members, our floor-to-wall interfacings, mechanical attachments, and so on. And we end up with a whole wall R value of approximately 1.8 across the board. Our high R wall, as we saw in the residential, less impact from each element moving from the nominal to the whole wall doesn't represent the same percentage drop in this example as we see in the other examples. Some pronounced dropping from nominal to the whole wall in the precast, but much different than how the same wall assembly looked in the code required, or the code wall for precasting in Calgary. So what conclusions can we draw from all of this work? Well, the first one is that the eaves-clad walls did not have to deviate from the requirements set out in their respective standards. The resulting thermal performance for the eaves represents details and practices that are typical for eaves project delivery today, including in our high wall context. By contrast, the alternative wall cladding systems had to deploy, in some cases, measures that do not represent standard industry practice or common industry practice, and in some cases go for quite a distance beyond what is typical today. This is a critical distinction because of the constructability challenges that emerge, in particular with our masonry veneer. For the residential wood frame walls, the eaves and the fiber cement clad walls showed significantly better thermal performance than our brick veneer. This is primarily due to the effects of heat loss through our shelf angles and lintels, as well as the contribution of heat loss by our masonry brick ties. For the commercial steel stud walls, the eaves and aluminum composite panel walls showed better performance than the brick veneer and the architectural precast. Challenges emerged for the brick clad walls and the architectural precast in achieving the thermal performance, again due to losses at shelf angles, brick ties, and in the case of precast, the floor to wall interface, as well as interfacings between the panel to panels themselves. One of the other aspects to emerge through this work is that our energy codes currently do not fully account or duly account for the loss of heat energy in areas such as window flanking. As codes incorporate a better accounting for the effects of window flanking and floor to wall and so on and so forth, it'll be important for all of the wall assemblies to come up with better strategies, if you will, to mitigate the loss of energy at these locations. For the high R walls, it's assumed that designers would implement effective installation detailing, and we can find those examples of this sort of detailing in passive house projects where the effects of window flankings are reduced to negligible through highly insulated returns. So with thermal performance in hand, we can now look at energy use. The energy analysis is based on hourly whole building annual simulations for each city, building type, and wall construction combination. This approach was chosen over modeling just a portion of the building, for example, 100 square meters for each wall assembly, for the following reasons. Hourly whole building modeling is currently the industry's state-of-the-art. It's an approach that has sophistication to address internal heat gains based on building type and usage and other considerations. It provides a better comparison for code compliance and adherence to certain standards like the Toronto Green Building Standard and the City of Vancouver Energy Modeling Guidelines. The simulation software used was eQuest 3 64-bit edition. Using whole building simulation, the model was able to account for a much broader range of inputs than would be accounted for if we just modeled a portion of the wall area. So we look at wall, roof, floor slab, windows, window to wall ratio, air leakage, floor to floor height, and the building footprint. Again, I will just repeat here that the window to wall ratio was 40%. Looking quickly to our commercial building, we have the same parameters and model inputs. However, the input values are slightly different in the commercial context relative to our residential one, as would be expected. the building typology entered into the model, we could then look at mechanical and electrical inputs. So domestic hot water, space heating and cooling, ventilation, corridor ventilation in our residential example, interior lighting and power density, and of course, receptacle loads. In terms of cost allowances, the study's interest was in the energy use assignable to the opaque wall area. To isolate this from the rest of the building's operations, the buildings were first modeled using what RDH felt was the highest level of thermal resistance they felt the software could tolerate. So the buildings were modeled with an effective R value of R200. The buildings were then modeled again using the whole wall R values from our study, as well as the high R wall, and the differences between those and the R200 walls assigned to the energy use for the opaque wall areas. I hope this gives you the picture of how they went about doing this. The results of the modeling then are as follows. And again, these are the annual energy costs assignable to the opaque wall area, not the annual energy costs of the building's energy use in total, but those relatable to the opaque wall area. So beginning in Vancouver, we have a total energy cost per square foot of 3 cents, 6 cents in Calgary, 6 cents in Toronto, and 7 for Montreal. When we move from our baseline wall, that is the wall that meets the prescriptive energy code requirement, to our high R wall, we reduce the cost in Vancouver to negligible. A cent per square foot could be argued as negligible for Toronto and Calgary, and 2 cents per square foot in Montreal. So a difference of 5 cents per square foot in Montreal, not insignificant when factored over 50 years. Looking now to our commercial building, we see greater savings between our baseline wall and our high R wall. So a difference of 7 cents in Vancouver. We go from a cost of 5 cents per square foot in Calgary to a negligible one. A negligible cost for our high R building, or that is the cost per square foot assignable to the opaque wall area in Toronto, become negligible in the high R versus 7 cents if we were just to meet the prescriptive code requirement. In Montreal, we go from an annual energy cost per square foot for our opaque wall area of 9 cents to a cost of 1 cent when moving to our high R wall. Looking now at the results in aggregate, that is, all things considered, no surprise that the results show that heating accounts for the single largest consumer of energy at 30 to 41% of total energy use. The models also captured some minor differences in fan energy use relatable to heating versus cooling conditions. The remaining energy use, including our hot water, plug loads, lighting, etc., was the same in all of our residential building scenarios. In a commercial building, once again, not a surprise that the results show that heating accounts for the single largest energy consumer at 19 to 29% of total energy. The study also shows that there is greater opportunity for cost savings when looking at the differences between our baseline wall performance and our high R wall construction. Although the heating demand is less for commercial buildings, the differences between the code compliant wall and the high R wall are much more dramatic, and that translates to greater potential for savings. Indeed, the study shows that heating costs can be reduced by 13 to 20%, not insignificant if you were to look at it in a life cycle context of anywhere from 30 to 50 years. So that wraps up this session of our series. I hope you found it informative and you'll come back and join us in part 3. In part 3, we begin the hard work of adding all of our inputs together. Our upfront construction costs, the repair and maintenance activities over a 50-year study period in both the residential and commercial context, and of course the outcome of the life cycle cost analysis itself. Until then, I'd like to thank you for joining me in this video series. See you next time.